My name is David Carter, and this is a talk that I put together for colleagues at work last week as part of a program that we ran during the International Climate Strike Week. We had a program of informative events of various kinds. I should stress that I'm not an expert in any of the topics that I'm going to be talking about, whether it's food or farming or forestry, and I do encourage you to look up the sources for yourself. They're not hard to find, and I'm going to reference some of them in this talk. So this is called Feeding the World Without Crashing the Planet. Can it be done? And it may all depend on the numbers, which I'll show you. Some alternative titles for this talk. I could have called it Feeding the World, Tackling Climate Change, Eating a Carnivorous Diet. Choose any two, can't have all three, or why beef is even worse than you thought. So to set the context, hunger is on the rise again after falling for many decades. The rise has only been slight so far. The bottom blue line, you can see the percentage of people malnourished in the world has gone up very slightly every year since 2015, and because the population's rising, the number of malnourished people has gone up rather more noticeably. Alarming news about food over the last few years. You may have seen this headline from a few years back. A senior United Nations official said that we have only 60 years of farming left if soil degradation continues. That's because generating 3 centimetres, just over an inch of topsoil through natural processes takes 1,000 years. But we're using it up fast with our industrial fertilizer-based farming practices. And if it continues, all of the world's topsoil could be gone within 60 years. And I find it hard to see how we could avoid being gone with the topsoil if that happens. And then a few months ago, there was a report from the Intergovernmental Panel on Climate Change called Climate Change and Land. They looked at desertification, land degradation, sustainable land management, food security, and things like that, and painted, I thought, quite an alarming picture. So I was surprised to see George Monbiot writing in The Guardian, taking them on for not sounding the alarm clearly enough. He said, we can't keep eating as we are. Why isn't the IPCC shouting this from the rooftops? In its crucial Land and Climate report, the IPCC irresponsibly understates the true carbon cost of our meat and dairy habits. And we'll see why that is later in the talk. It's for a reason that might not initially occur to you. It certainly didn't occur to me. And then maybe you've seen this guy, Roger Hallam. He's one of the founders of Extinction Rebellion. He was interviewed recently on the BBC's Hard Talk programme, where every interviewee is given a hard time. Roger was no exception. One of the things he said was the capitalist system, the global system that we're in, is in the process of destroying itself, and it will destroy itself in the next 10 years. The reason for that is because it's destroying the climate. The climate is what's necessary to grow food. If you can't grow food, there'll be starvation and social collapse. So that sounds pretty alarming. And I wondered, is he actually right? Because much as I admire Roger, I think he does have a tendency to see things in very black and white terms, and he sometimes states things as if they're certainties when there's really quite a lot of uncertainty attached. So I decided to dig into the numbers. This is a complicated area, and on the right you can see a diagram from somewhere or other, I forget where, of just what all the components of the climate and ecological emergency are, and you'll see it's very complex indeed, with all sorts of things happening and affecting each other, feedback loops and all the rest of it. And this talk is really about the things inside that red line: land shortages and food shortages, and to some extent water. And food production is linked to a number of other things. Most obviously, population. Obviously, the more people we have, the more food we have to find for them. Land use, because growing food requires land. Climate change, both because food production causes climate change and because climate change affects our ability to grow food. And finally, water, because water is required for growing crops and for animals as well. And all of these things interact in multiple ways. So it is very complex, and I hope I'm not oversimplifying things too much, but this is just to alert you to the fact that this is one aspect taken perhaps rather arbitrarily, but inevitably out of context, in an effort to make some sense of it. I'd like to introduce a helpful concept, a new as far as I know, unit of area called the MISC, just to avoid having to talk in terms of millions and billions all the time, at least when it comes to areas. We can have the MISC, which is defined as 1 million square kilometres. That's almost exactly the total area of France and Germany combined. The area you can see in the orange and the green there. In terms of more conventional measures, it's 100 million hectares and about 250 million acres, or 390,000 square miles. And I'm using the MISC so as to avoid having to use all those other smaller measures and all the millions that go with them. So what are all of our MISCs used for at the moment? Well, the total land surface of the world, including every kind of land, deserts, Antarctica, all sorts of places, is 149 MISCs. And most of that, about 2/3, 104 MISC, is habitable in some sense. So it's either shrubland or forests, or it's used for agriculture. And a little bit is used for cities, but that's small compared to the total, so I've left it off. What you should remember from this is the forests currently are using 39 MISCs, and agriculture is using a massive 51, so that's almost half the habitable surface. And of that, livestock is using 40 MISCs, so that's the vast majority of it. Most of that is used in the obvious way for pasture for animals, and some, about 4.5 MISC, is used for crops that the animals will eat. And a smaller amount, I think it's 9.5, is crops for humans, and there's a little bit used for biofuels and industry, and that's 1.5. So the takeaway from this is that a lot more land is used for livestock to feed people indirectly than is used for crops to feed them directly. But to zoom in on the bottom left of that previous picture, on the left here you can see in purple that land that's used for livestock is much bigger than the land that's used for crops for people. But even so, the vast bulk of the calories that people consume comes from the crops grown in that little green area. And also 2/3 of the protein that we consume comes from those plants. So you can see that livestock is a very inefficient way, just viewing it as a means of producing food for people. It's a very inefficient way to produce food. So 77% of the land produces only 17% of the calories and 33% of the protein. And that turns out to mean that crops are 7.7 times as efficient at producing protein as eating animals is. You probably can't see that bottom right hand number because of the way that PowerPoint works, but it is 7.7. Population, of course, is going up. The black line here, you can see schematically how the world's population has grown, especially over the last 70 years or so. We're now on about 7.7 billion, and of course we don't know quite how it's going to go after this. The UN has 3 projections that it uses in its forecasts: a low, a medium, and a high. And since I have no idea which is right, I've chosen the medium one to base a lot of this talk on. So the median projection sees us rising to 10 billion by 2050, which is about 40% more than we have now, and up to 11 billion by 2100. So how are things going to look in the future? So at the moment, you can see the first two columns. These are numbers you've seen before in the italics. We're using 40 miscs for animals, 9.5 for crops. And as we saw, using it for crops for people is a much more efficient way of feeding people than growing it for animals, which we then eat. And the bottom row, MISC 2100, that's allowing for the expected increase in population to 11 billion, and assuming that we still have the same mix of agriculture and the same practices that we have today. So because the population will be bigger, our 40 miscs for animals will need to increase to 57, and our 9.5 for crops will need to increase to 14. And adding those together, we currently use 49.5, but we'll need to use 71 in 2100. Quite a lot more. Where's all that land going to come from? Well, that will be a problem, as we'll see, but here's the light at the end of the tunnel, perhaps. If, to take an extreme case, we all went totally vegan, didn't eat any more meat or dairy, we get the numbers in this crops vegan column. So if we just eat what we can grow directly, obviously we'll need a bit more land for crops. So instead of 9.5 miscs today, we'd need 14.25, and in 2100 we need 20 miscs, but that would feed the whole human population. So that is clearly doable, because 20 is a lot less than the 49.5 we're currently using. We should, however, allow for the fact that, as we saw earlier, we only have 60 more harvests left if we carry on farming the way we are. So we need to go organic, effectively, or sustainable, or whatever. There are various different terms, conservation agriculture, and they all mean different things, but they all involve a slight reduction in yield on average, we think. So there was a study done by the EU which reckoned that, looking across a number of surveys or pieces of research, organic yields were on average about 80% of conventional, which isn't bad considering all the advantages they have in preserving the soil and avoiding the use of nitrogen-based fertilizers and so on. So because they're slightly less efficient, instead of the current 14 miscs, we'd need 17.8, and in 2100, instead of 20 miscs, we'd need 25.3. So you'll see I've put 71 in red for the current mix of methods in 2100, because that's a lot more than the current 49.5, and I put 25.3 in green because that's a lot less. So look at what that means. So as we saw before, our current world forests are 39 miscs. If we feed the world with our current practices in 2100, we're going to need 21.5 miscs more. So where are we going to get that from? Well, probably not from the shrubland, because that's only semi-fertile. Presumably, if it can't grow trees, we're going to have a hard time growing crops there, mostly. So it's going to have to come out of the forest land. We'd have to cut down over half our forests, and as I'm sure we know by now, cutting down trees in general isn't a great idea. So how does it look with a vegan diet and organic agriculture? Well, we saw that would require fewer miscs than we're currently using, 24 fewer in fact, and if we were able to forest all that freed up area, that would mean we could grow 60% more forest, which seems like quite a good thing. Now this involves quite a few simplifications. It may even be simplistic, so I'll just list what some of the assumptions and simplifications are, so you know what I'm doing here. As I've said, I'm assuming that the population is going to follow the UN's median projection and peak in 2100. I'm also implicitly assuming that some other things either won't change or will cancel each other out. So we do see some yield increases due to technology improvements over time, and they will presumably continue. But we're losing farmland and we're seeing yield reductions because of climate change. And I'm assuming, for the sake of argument here, that those two effects will roughly balance each other out. So the amount of food we can grow will not change due to either of those things. I'm also, perhaps more seriously, assuming that all farmland could, in principle, be converted to forest and vice versa. And that may well not be true, but I think it is true for a lot of the land. So I think most of this does go through. I'm also assuming that we won't have a major disaster in terms of our the pollinating insects, which are really important for a lot of kinds of crops. There's been some very alarming evidence of insect collapse over the past year or two. It's been going on for decades, and I'm assuming that that won't continue to such an extent that crop yields are affected. I'm afraid that is actually not a safe assumption. It is something to worry about, and it's one more reason why we need to stop using pesticides in particular. Speaking of insects, I'm also assuming that we won't eat a lot of insects. There's been some interesting work on using insects for food, drying them out, grinding them up, or whatever. Apparently they are nutritionally quite good. Personally, what I can say about that is I'm fully in favour of insects forming part of people's diet, as long as they don't form part of mine. Maybe you feel the same. I think they will face a certain amount of resistance. They could help a bit, although their carbon footprint is not zero. There's also been some interesting work done on sunlight-powered bacterial food. The idea is you get bacteria powered by sunlight to use photosynthesis to grow stuff that we can eat, and that looks quite promising. At the moment, it's not being done anywhere near its scale. It's being researched for possible use on a human mission to Mars. But who knows, if it could be scaled up massively, that might help us too. So what about this trees thing? If we did go vegan and organic and free up lots of land and grow trees on it, how much good would that do? Well, it does seem we have the technology, although it's not our technology, obviously, it was there all along. So looking at the literature, forests can store something between 100 and 250 tons of carbon per hectare. And typically, a sort of figure in the middle of that range is about 170 tons. It depends on the part of the world and the type of land, not surprisingly, but 170 is typical, so I'll take that as the average. 170 tons per hectare is equivalent to 17 gigatons per misc. And when we're talking about carbon in the atmosphere, the unit we want is gigatons, really. There is currently in the atmosphere about 300 gigatons of carbon, which is anthropogenic in the sense that it would not be there if there weren't people around, having caused the Industrial Revolution and all that followed. So historically, there was 300 gigatons less than there is now. How many trees would it take to suck all that back out of the air? Well, it actually, theoretically, could be done. So 17 gigatons per misc and 300 gigatons, divide 300 by 17, and you get about 18 miscs of new forests. And remember, we saw that by going vegan and organic, we could release 24 miscs, which is more than 18. So assuming that the forests are actually feasible, that it's possible to grow forests on the freed up pasture lands that the livestock don't need anymore, then this could be done. But it's quite tight. So 18 is not that much less than 24, and this only accounts for the CO2 that we've already emitted. And obviously, even if we get a really radically ambitious agreement at the vital COP meeting in Glasgow at the end of next year, it's unlikely that we'll suddenly stop emitting CO2 altogether. So there will be a tail-off, fast as possible, but there will be more CO2 put up there. But we do have to reduce very rapidly, otherwise it will take more miscs of forests than we can do. Of course, if population growth is higher than the median projection, then we're in trouble. If it's lower, we've got a bit more wiggle room. So now I'd like to get on to what George Monbiot says. And before I do, I just want to tell you or remind you about the distinction between actual cost of something and the opportunity cost. So supposing you have £1,000, there are two things you might do with it. You might put it in a zero interest account, which isn't just zero interest, it also charges you 0.5% on your money. So the actual cost of putting it there for a year, say, is £5. But say your alternative was that you could have invested it safely at 10% interest. Well, that's unlikely these days, but for the sake of argument, let's assume you could have done that. But you don't. You put it in this zero interest account. Then the money that you've foregone, the 10% you could have earned, is £100. So we say that the actual cost of your decision was £5, but the opportunity cost was 100. It's a kind of counterfactual thing, but just as important, arguably. So with that distinction in mind, let's look at what happens with the animals and the trees. So here are some numbers. Now, these are two displays of roughly the same sort of information. Over on the left, from a study by Chatham House, we've got greenhouse gas emissions per kilo of meat. So these numbers are ratios. The number of kilos of carbon dioxide that it takes in terms of actual emissions to produce 1 kilo of meat. So it's a ratio. It's 56.6 kilos on average, they reckon, for 1 kilo of beef. For lamb, it's still pretty bad, 31.3. For other kinds of meat, pork and chicken, it's 8.8 or 7. And for other kinds of food, it's less. So clearly beef, and to a lesser extent lamb, are very costly in terms of greenhouse gas emissions. And you can see similar information in a slightly more sophisticated form on the right. This diagram is from a paper by Pora and Nemecek from Science last year that had quite a big impact. It makes the points that these figures vary depending on how and why the animals are farmed. So low impact beef can be a lot lower impact than high impact beef. And the same with all sorts of other kinds of food. But still, beef and lamb come out as fairly high impact. Those are the actual costs. Those are like the 0.5% charge that you pay on your money. But what about the opportunity cost? So George Monbiot says 1 kilo of beef protein has a carbon opportunity cost of 1,250 kilos, and in that context he's talking about CO2, not carbon, okay, because only part of the CO2 is carbon, the other part is oxygen, and in terms of weight the CO2 is only a minority. So 1 kilo of beef protein is about 4 kilos of beef, because beef is about 1/4 protein. In the UK, if you're going to eat British beef, it's not so bad. We have carbon-rich soils, so apparently it only takes half as much carbon opportunity to grow the beef in this country, presumably because the cows need less land, because they're eating grass off richer soils. So, crunching the numbers, one typical serving of beef, which is about 250 grams or 1/4 kilo, equates to 312 kilos of CO2, or if it's British beef, it's half that, 156 kilos. That's the opportunity cost, okay? That's what could be sequestered by the trees if we had trees there instead of cows. The actual cost for your 250 grams serving is quotes only, it's still pretty big, but it's only about 10 kilos. And 10 is a lot smaller than 156, let alone 312. So in other words, the opportunity cost for beef in terms of CO2 emissions is 16 to 31 times the actual cost. It's a huge ratio. And if you calculate over the whole typical UK diet, which is a mixture of different kinds of meat, fruit, vegetables, and so on, the opportunity cost of the average UK diet is about 9 tonnes of CO2 per year, and that's roughly equal to our total actual carbon footprint, not just from food, but from heating our homes, driving around, flying, all the rest of it. So in other words, this opportunity cost is absolutely enormous, and that's why George Monbiot says we can't keep on eating as we are, and the IPCC is understating the true cost. Of course, this assumes that we would plant the trees if we all went vegan, and we have to make sure that happened, but you see his point anyway. I'll briefly talk about the story for water. This talk isn't mainly about water, but it's an important factor in all this as well, and it's rather similar to the land story. So by 2025, 2/3 of the world's population may face water shortages. Of course, quite a lot of them are already facing water shortages, mostly a lot worse than in the UK. In Cambridge, where I am, we're already seeing growing problems with the growing population in the area needing more and more water to be used, and the river and the groundwater can't cope, and we're going to hit real trouble in a few years, which the planners don't seem to have woken up to or aren't admitting to. Anyway, globally, the entire human race, between us all, we use 10,700 cubic kilometres of water per year. So to scale that down to human level and making it per day rather than per year, that comes to about 4 cubic metres per person per day. So that's not just the water that you actually use in your house for drinking, cooking, washing, and so on. It's everything that's used for you to supply your lifestyle. So 70% of it is for agriculture. You never see it, but you do end up benefiting from it. And looking at our two main kinds of meat that we're focusing on, beef requires 15,000 cubic metres per tonne to produce of water, this is. Lamb takes 10,000 cubic metres of water per tonne. And making that human scale again, for one serving, 4 cubic metres of water for a serving of beef, 2.5 cubic metres for a serving of lamb. So you'll notice that if you have a beef meal, the water that it's taken just to produce the beef for your meal for that one day is the same as the water that's used for the average person on the world for everything for that day. So that's clearly well over the average. It turns out that most water use for animals is via crops. It's about 1/3 of the total. The rest is used in a more direct sense for crops for people. But still, to support the 11 billion people we're expecting to be here by 2100, without extracting more water for agriculture, which we don't really have, we will need to go nearly vegan, for roughly the same sort of reasons as we've seen for land use. So what can we conclude from all this? So it's sort of semi-optimistic, maybe. Climate change will not cause mass starvation, at least not globally, in the next 10 years, unless we hit a serious tipping point in the meantime, which is entirely possible. So the Arctic ice melt could set something spiralling beyond what climate science thinks is at all likely at the moment. We could have a lot of methane bubbling up from under the permafrost in Siberia. Those are probably the two main threats, but there are others as well. If any of these tipping points happen, we're in very, very serious trouble indeed. And food is not the only thing that we'll have to worry about. But still, in the next 10 years, I would say this seems relatively unlikely, although not impossible. So in that sense, I think Roger Hallam is probably wrong, although if he does turn out to be right, I won't be completely and utterly surprised. However, I do think that there will be mass starvation in the next 80 years by 2100, or even in the next 30 years by 2050, unless we switch to a largely plant-based diet. So that's because of the numbers I've prevented. We have a choice. We can do two of the three things, as I said. We can go plant-based and plant trees, and then we might be okay. Or we can carry on as we are eating meat, those of us who can afford it, and then either we feed everybody by cutting down a lot more trees, so everybody gets fed, but we crash the climate, or we don't cut down the trees, we might still crash the climate a bit later, and a lot of people starve. So neither of those seem like great options, and surely the only sensible one to go for is to radically reduce our meat and dairy consumption so that everybody can eat, and at least we have a chance of avoiding the worst of climate chaos. So slightly very qualified, optimistic conclusion. If we switch to a plant-based diet and plant lots of trees in the land that's freed up, and if we curb emissions radically from this point onwards, and if we don't hit a serious climate tipping point, and if all the pollinating insects don't die out, and probably a few more things as well, like no major wars and no epidemics and everything else, with a bit of good luck like that, we can feed everyone and restore CO2 to safe levels by the end of the century. So it's not impossible to do that. It does maybe lie within our power if we get a bit of luck. Whether we'll do it, I don't know, but we do seem to have that option available to us.